These are notes for Chapter 5. Um, chapter 5 is all about the periodic table, and most of this chapter will be very easy. You've already had a lot of it. So Section 2, where it talks about electron configuration, I've already shown you how to relate the electron configuration to the periodic table. That's how we learn how to do them. So most of Section 2 will be a review. So really Section 1 and 3 are the only ones that have new material. Right. In Section 1, we talk about the very first periodic table, and it was put together by a guy named Mendeleev. He came up with a periodic table that he put in order of atomic mass. If you look at the periodic table, for the most part, this is still true to the one we currently have. There are just a couple of elements. So for example, cobalt and nickel. The mass for cobalt is actually heavier than the mass for nickel, even though cobalt comes before nickel on the periodic table. So there are just a couple of little exceptions like that have the periodic table out of order from mass. But another thing that Mendeleev did, his periodic table was vertical instead of horizontal like ours. So instead of going from left to right, his went from top to bottom. But one thing that we'll notice in the periodic table is the actual word periodic. So it means a repeating pattern. So it doesn't matter what you call that chart of elements, it has to have the word periodic in it. So periodic table, periodic chart of elements, periodic table of elements. It doesn't matter which one, but it has to have the word periodic in it to show that we have these repeating patterns. Mendeleev's periodic table did have some repeating patterns, but not quite as many patterns as what we currently have. Another thing with Mendeleev's periodic table is there were a couple of gaps. So once he put in all the known elements, there were missing spots. And so he was actually able to make predictions about these missing elements that have yet to be discovered. And if you look at a picture of it in your book, the predictions that he made and the actual elements are really close to correct values. So these three, gallium, scandium, and germanium, are the three elements that he made predictions about. These are the names that he gave them in this first column. So now this column says predicted properties. So the density of gallium, he put as 6. Well, it's actually 5.96. Density for scandium, he put 3.5. Well, it's 3.86. Density of germanium, he put 5.5. It's 5.47. So his predictions about these undiscovered elements were extremely close to the actual values. So there are things that we can determine about an element just by its location on the periodic table. So we get to the 1900s, and Henry Moseley comes along, and he sits down and kind of rearranges what Mendeleev had. So it's kind of like playing element solitaire. He wrote down all the properties onto cards, and he laid them out. And he found a better way to arrange the periodic table. So instead of doing it by mass, Henry Moseley put together the periodic table by atomic number. And instead of putting them in columns from top to bottom, he went from left to right. So this kind of leads us to the periodic law, and it says that these patterns that we find, or these properties that these elements have, are in order of function by their atomic number. So as the atomic number increases, some of these periodic properties will also increase or decrease. So make sure with whatever term you use to label that table or that chart, it has the word periodic in it. So it's an arrangement of elements in order from atomic number, so that elements with similar properties fall in the same column or group. So not only do we have patterns going from left to right, but we also have patterns going from top to bottom. And we'll look at all of those in Section 3. Section 2 I'm kind of going to move quickly because most of the stuff you already know. All right, periods. These are our rows in the periodic table. They go from left to right. The length of each period varies depending on what row it is. So some of them only have the S block and P block. Some are SPD and some are SPD and F. The very first group, so the very first column of the periodic table, these are the alkali metals. One of their properties is we go from top to bottom, they're more and more reactive with water. So if I put lithium in water, it will spark and fizz. But if I throw some sodium in water, it's going to spark and fizz a little more. If I throw some potassium in water, it's going to spark and fizz. And if I throw it in a pond, it will actually spray water up in kind of a mushroom cloud type formation. You should YouTube some videos with potassium in water. They're pretty neat to watch. All of those elements, since they're so reactive with water, they have to be packed in mineral oil or kerosene, so that way moisture from the air will not cause them to react. They all have properties of metals, so they're shiny, they conduct electricity, extremely soft, every single one of them, so we could actually slice them up with a butter knife if we needed to. Group 2, these are the alkaline earth metals. Most of these can be found in the upper crust of Earth's soil. Most of them are not soluble in water. A lot of them are very common, so you'll notice that they are minerals and nutrients that we need in our regular diet. All right, the d orbital, these are called transition metals. So this goes from groups 3 through 12. These elements are all metals. They are all excellent conductors of heat and electricity. They are malleable, they are ductile, they have luster. Remember, malleable means that we can bend them or shape them. Ductile means that we can draw it into wire. So continuing across, we call the s orbital and the p orbital together. These are the main group elements. So you'll notice when we start learning how to write chemical names and formulas, we're not going to use a whole lot of the d orbital. There are maybe 10 total that we would use regularly out of the d orbital, and that's being kind of generous. So most of the elements that we will deal with come from the S and the P. So we call these main group elements. But as we continue across the periodic table, we get to the stair-step line. These elements are called the metalloids. They separate our metals from our nonmetals. If the element touches the stair-step line on two sides, it's considered a metalloid. There are some exceptions to this. So aluminum is always a metal. A lot of times you won't see astatine, AT, I think it's number 85. A lot of times you won't see it labeled as a metalloid. But these elements have properties of both metals and nonmetals. They can conduct heat and electricity, but not very well. They can't conduct a whole lot of heat or electricity. They're very brittle solids, so they are not malleable, they are not ductile, and they don't have luster. If we keep going across, so above the metalloids, above that stair-step line, we have our nonmetals. Most of them are gases at room temperatures. The solids at room temperature are very, very brittle, so most of those are powders. Group 17 is the most common group of the nonmetals. These are called the halogens. It's fluorine, chlorine, bromine, and iodine. These are very, very reactive elements. So example, fluorine is so reactive, it can actually bond with a noble gas. And we know those noble gases, they have their 8 valence electrons they don't really want anymore. But fluorine's nucleus is so strong, it can actually cause the electrons from a noble gas to bond with it. So group 17 elements are something that you will be very familiar with. The halogens usually form salts with group 1 elements, and these are referred to as halide salts. And then the very bottom of the periodic table, we have the rare earth metals, and they are the lanthanide and actinide series. The lanthanides look just like regular metals. They'll be shiny. They can conduct heat and electricity. The actinide series, these elements are mostly man-made, as they were created in a lab. And just about all of them are going to be radioactive, so it's something we definitely won't be handling in the classroom. All right, section 3. So now this is when we get into some periodic patterns. There's a worksheet that you have that's actually called periodic patterns, and this would be a good time to pull it out. This is where most of your information is going to come from. So the atomic radius is 1/2 the distance between the nuclei of identical atoms. So we measure from the nucleus of one atom to the nucleus of the next adjacent atom. This is how we come up with our atomic radius. As we go across the periodic table, the atoms tend to get smaller. So as we go from left to right, the atomic radius decreases. As we go from top to bottom, so as we go down the periodic table, the atom tends to get larger. The reason being, as we're going from left to right, we're not adding any rings to our atom. So if we're on the 3rd row of the periodic table, if we're talking about one of these elements, it has 3 rings. As we go from left to right, we're adding electrons, we're adding protons, we're adding neutrons, but we're not adding any more rings. So these electrons can't get any further away from the nucleus. Well, the nucleus is gaining more protons as we go across. So the nucleus is becoming more and more positive, but the electrons can only go on that 3rd ring. They can't move further away. So because we have so many protons, so much positive charge inside our nucleus, it actually pulls those electrons closer to it. So it's kind of like tightening a belt around the atom. So as we go from left to right, our atom's getting smaller. As we go down the periodic table, with each row, we're adding another ring to our atom. So now these electrons can spread out and get further away from that nucleus. That explanation will pretty much relate to just about every other pattern that we're going to talk about. So for ionic radius, remember an ion is an atom that's given away an electron or has gained an electron. This will cause a change in size as well. But we'll notice it follows the same pattern for the atom. So as we move from left to right, the ion gets smaller. And as we go from top to bottom, the ion gets larger. All right, so talking about ions, we have something called ionization. And so this is just a process that an atom goes through when it gains or loses an electron. We have ionization energy, and we have numbers that correspond with ionization energy. So ionization energy is the amount of energy that it takes to remove an electron from an atom. Well, the nucleus is what's holding that electron in. So if we take away one electron, that means we have more protons now. So that means the electrons are even more attracted to our nucleus. So the first ionization energy is going to be the lowest when we take away the first electron. When we try to take away the second electron, we have a sharp increase in ionization energy because the nucleus has more control since we have more protons than we have electrons. And then the third ionization energy will be even larger because we'll have 3 more protons than we have electrons. So as we move across the periodic table, our ionization energy is going to increase. It's going to take more energy to remove each electron from that atom. And that's because our atom's getting smaller. Those electrons are moving closer to the nucleus, and so it's going to be harder to pull them away. As we go down the periodic table, our ionization energy is going to decrease. So as we add rings, as we add energy levels to our atom, it's moving the electrons further away. So the nucleus doesn't have as much control of those electrons the further they are away. So now it's easier to pull those electrons off that atom. So the ionization energy is going to decrease as we go down the periodic table. This trend will be good for you to look at. We're going to do a graphing activity at the end of this chapter, and you'll want to refer back to this, but you can also find it in your book. All right, electron affinity. So this is how we calculate an energy change when an electron is gained by an atom. So now instead of talking about losing electrons, we're talking about gaining electrons. So it increases as we go from left to right. So the nucleus is much larger, it's more positive, so it's able to pull electrons away from other atoms. And then electron affinity decreases as we go down the periodic table. And that's because our atom's getting larger. Ionic radii, I've already talked about this a little bit. So this word is cation. It is not a cation. Do not call it a cation. People will think you're uneducated. It has a T in it. So T, that looks like a plus symbol. So cations have a positive charge. Anions have a negative charge. Cations are going to come from the left side of the periodic table. These are going to be our metals. Anions are going to come from the right side of the periodic table. These are our nonmetals. I've already talked about the radius. Valence electrons. This is probably a term that's familiar to you. Valence electrons are the number of electrons on that outermost ring of an atom. So we're looking at how many electrons are on that last row. If you look at a noble gas electron configuration, if you add up your exponents, that will tell you the number of valence electrons for that atom. Another thing that you can do is you can look at a periodic table. So everything in row 1, their electron configuration is going to end in S1. They all have one valence electron. Group 2, the second element on that row, they have 2 valence electrons. We skip rows 3 through 12 because their number of valence electrons can change. We get to group 13. They have 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5. Group 16 has 6. 17 has 7. And group 18 has 8 valence electrons. All atoms want 8 valence electrons. And sometimes they give away electrons so that they can go to the next lower energy level. And some atoms gain electrons to get them all the way to 8. When we give away or gain electrons, this determines our charge. So for sodium, it has 1 valence electron. We have to ask ourselves, does it take less energy to give away that 1, and then we can have 8 electrons on our second one? Or should we try to gain 7 more? Obviously, it's easier to lose 1. And the same thing happens to all of those elements in the very first column. So group 1 elements all have a -1 charge. In group 2, we have to ask ourselves the same thing. They have 2 valence electrons. Can I give away 2 electrons, and then I'll have 8 electrons on my second energy level? Or should I try to gain 6 more? That's going to take too much work. So we're going to give away 2 electrons. I'm sorry, that should be a positive charge. If we give away electrons, we have a positive charge. So here we should have a positive 2. We skip groups 3 through 12 because those numbers can vary. Group 13, we have 3 valence electrons. It's easier to give away 3. So I'm going to put a plus 3. So everything in this column has a plus 3 charge. In group 14, it can vary. It takes the same amount of energy to gain 4 or lose 4. So we put plus or minus 4. In group 15, we have 5 valence electrons and we want 8. So it's easier for us to gain 3 electrons than to try to give away 5. So for gaining electrons, we're becoming more negative. So this is a negative 3 charge. Group 16 has 6 valence electrons. It's easier to gain 2 electrons than give away 6. So since we're gaining 2 electrons, it's a negative 2. Group 17, they will gain 1 electron. So they become a negative 1 charge. And the noble gases, they already have 8 valence electrons. So they want 0. They will not have a charge. I would add these charge numbers to your periodic table in your text or in your notebook. All right, so now we're back to notes. Electronegativity. I'll refer to this a lot for the rest of the year. So this is a good term to know. Electronegativity is the ability of an atom to attract electrons from other atoms. So what this means is the nucleus is so positive for that ion that not only can it hold on to its own electrons, but it can snatch up electrons from other atoms. So our electronegativity increases as we go across the periodic table. And this should kind of make sense because our atom's getting smaller, but our nucleus is gaining more and more protons. So now we have a very large nucleus inside a very small atom. So that very large nucleus can snatch up those electrons. As we go down the periodic table, however, our atom's getting larger. Our nucleus is not as big, but we keep adding rings to our atom. So our electronegativity decreases as we go down the periodic table. And that brings us to the end of chapter 5. There are some terms on your periodic pattern worksheet that are not in this chapter. So you'll just have to Google, look them up on the internet for their definition and their periodic trends.